In the second part of 4.9, I'm going to continue to show you some more techniques for finding antiderivatives and hopefully help you with the process of thinking backwards. So this second example, we're going to be taking the antiderivative of a fractional expression of a rational function. 4x to the 19th minus 5x to the negative 8 all over x squared. And of course I need to say with respect to which variable we are taking the antiderivative. By the way, I didn't mention up above, I'm going to go back to the last video for a second. In this example, I was taking the antiderivative of just a constant 2, and so I needed to add a variable back in, which happened to be x. The only reason that I knew to write an x there and not a t or a u or a v or some other variable is based on that given information within the problem, that you're doing it with respect to x. So hopefully that's obvious. Back to this other example down here. What I need to do is I need to constantly rewrite my antiderivatives or my integrals as much as possible if I can. I need to write it as the sum or difference of power functions. And so remember, power functions are in the form x to the p. As long as I have it as a sum or difference of power functions, then I can use those same three rules, the power rule, the sum rule, the constant multiple rule. So let's take this and rewrite it. So I'm going to write it as 4x to the 19th over x squared minus, put parentheses around the whole thing, 5x to the negative 8 over x squared with respect to x. Okay, I'm going to continue to simplify that. So 4x to the 19th divided by x squared, I can just subtract my exponents there. So that would be 4x to the 17th. And then here, negative 8 minus 2 would be minus 5x to the negative 10th. So I'm getting closer. I at least have two power functions, but I'd like to separate them using the sum rule as well as pulling the constants out front. So I'll have 4 times the antiderivative of x to the 17th with respect to x, and I'll subtract 5 times the antiderivative of x to the negative 10th with respect to x. So at this point, I'm ready to use my rules and actually do the integration or find the antiderivatives. So power rule here, I'm going to add 1 and divide. So that'll be x to the 18th divided by 18. Multiply your constant multiple, add c. And then over here, I'm going to add 1. Remember, adding 1 to negative 10 becomes negative 9. Divide by negative 9. Alright, let's clean that up. I'm going to jump back over here just because I don't have any more paper space. 4 and 18, this fraction right here can be reduced. Each is divisible by 2, so that's 2/9 x to the 18th. The constants, c1 and c2, I can combine and add to the very end. And then over here, I've got this fraction, negative 5 over negative 9, so I can add 5/9 x to the negative 9 plus c. So that's a good answer. You may also, especially in my math lab, think about writing this x to the negative 9 as a positive x to the 9th in the denominator, which are equivalent. But either way, that is the antiderivative or the answer to this integration problem here. Let's keep going with some more examples. Flip my paper here. All right, third example. This one I've got some z's. So over the years I've learned that putting a little dash through my z helps me distinguish that from a 2. Before I actually do my integration, let's rewrite this. So I need to rewrite it as the sum or difference of power functions. And right now it's written as a product of 2 binomials, so that doesn't work for me. So what I want to do is I want to FOIL this out. And so that'll give me 2z cubed minus 5z squared plus 2z minus 5. Now I no longer have products, but I have sum and differences of every term. So let's just use that constant multiple rule and that sum and difference rule and write out each term. So in the first term, I'll pull out the constant multiple of 2. And in the second term, I'll pull out a 5. And in the third term, I'll pull out a 2. Whoops, I forgot my dz here in this last one. That's a common mistake. Just try to watch it, catch yourself. And then in the last one, I'll pull out a 5, which leaves me with a 1 dz. And so in that case, it might be just as easy to leave the 5 in. Let's use the power rule. So I'm going to add 1 and divide, multiply by my constant multiple. Don't forget to add c. Again, you can do it at the very end, you just can't forget about it, which is easy to do. Then we'll have minus 5 times z cubed over 3 plus 2z squared over 2 minus 5z. And I did continue to forget to add constants, although it doesn't really matter, because in the end, all of those constants are just going to add up into one final constant. So let's simplify each term, and then we'll have a constant c at the end. So 2/4 is going to reduce to 1/2. 5/3 doesn't reduce. The 2's cancel, and then minus 5z. So that is our final answer for this problem. Alright, so that's pretty much all of the tricks that you're going to see when you're working with power functions. Sometimes you need to divide each term and separate it out. Sometimes you need to take the 2 multiplied binomials to create sum and difference terms. But those are pretty much the only tricks that you're going to run into with those types of functions. When I move on to my next type of function, you're going to see something completely different. So here, let's take the antiderivative of secant squared x with respect to x. So now these are a little bit trickier. Now you have to think backwards about trig derivatives. And by the way, if you look at the PowerPoint for 4.9, you're going to see a whole list of trigonometric derivatives and antiderivatives just to help you. So sometimes if you're stuck, you can look at that list and it'll help jog your memory. So here, you want to ask yourself, what or which trig function, which trig function's derivative is secant squared x. So which function would you take the derivative of and get an answer of secant squared? And hopefully you do have that memorized, and hopefully it comes to you pretty quickly that this one is actually really easy. It's the tangent function. So that means that if you took the antiderivative of secant squared x with respect to x, you'd get an answer of tan x plus some constant c. Always check your answer, reverse the process. If you take the derivative of tan, will it in fact give you secant squared? And it does. So these can tend to be a little harder because there's no formula the way that there is with the power rule or the power functions. You can't just add 1 to the exponent and divide every time. Here you really have to sort of think about everything you have memorized and put it all together. So that one was really straightforward. This one isn't. So in this one, we're trying to take the derivative of the sine of 3x dx. And so this one's tricky because of the 3. So the first thing you should ask yourself is, which trig function or which trig function's derivative is the sine of x? And the answer is that there isn't a trig function that has the derivative of sine of x, but there is one that has a derivative of negative sine of x. Remember that the derivative of the cosine of x is negative sine x. So if I want positive, we'll think about it this way. Taking the derivative of negative cosine x would give us that positive sine x. So I know at least I need a negative cosine of x in my antiderivative, because the derivative of negative cosine would give us that positive sign. The problem is the 3. So you have to think that 3, when you're taking a derivative, would require the chain rule. So in this case, we have to basically undo that chain rule. So let's start off with this. Let's do a little bit of guess and check, which is sometimes what you have to do with these kinds of antiderivatives. Not so much with the power functions, but definitely here. So let's say that I were to take the derivative. I'm going to guess different derivatives and check to see if it gives me the antiderivative that I'm looking for. So let's say that I were trying to take the derivative of negative cosine 3x, because I know I have to have a 3 in there somewhere. Let's see what answer that gives us. So remember, I'm doing derivative here. So the derivative of cosine is negative sine. I want the opposite of that, so that'll be the positive sine of the inner function, 3x, times, remember this is the chain rule, times the derivative of that inner function, so times 3. So that would give me 3 sine 3x times 3. Whoops, I already wrote the times 3. Sorry about that. 3 sine 3x. So you want to compare that. We guessed. Let's check. Is that what we wanted in terms of our antiderivative? And it's not. We wanted everything but the 3. So think about, what would you have to have divided this original function by so that this 3 would go away? And the answer is that you would divide it by 3 in order to make that go away. So, all that said, the antiderivative of sine of 3x is negative cosine 3x over 3. And once again, you could check that by taking its derivative, and you'll find that it does give you what you started with. So a lot of times when you have a chain rule involved or a constant multiple on the inside of a trig function, you have to divide by that constant in order to undo it.